Imagine you are teaching a child to identify a fruit by showing them a basket of apples and oranges. You don't give them a complex rulebook, you simply show an image and say, "This is an apple." This is called supervised learning, where the AI learns from a labeled data set. In our code, we represent this as a list of inputs and their corresponding correct answers. A common mistake is thinking the AI understands the fruit. It actually just learns to associate patterns with labels. At its heart, machine learning is just finding a mapping function. Think of it like a translation dictionary, where an input X always leads to an output Y. Our goal is to create a Python function that can take a new, unseen input and map it to the correct label based on what it saw before. We start with a simple dictionary to simulate this mapping. Beginners often confuse the mapping process with hard coding, but in real AI, this mapping is discovered automatically. Now that we have a mapping, we can make a prediction. This is like the child seeing a new red fruit and remembering that red usually means apple. We create a predict function that looks up the input in our learned mapping. If the input is missing, the model fails, which is why real AI uses probability instead of exact matches. Notice how we separate the training phase from the prediction phase to test the model's logic. What happens when the AI sees something it has never encountered, like a yellow fruit? In our current simple mapping, the AI just says unknown because it cannot generalize. Generalization is the ability of an AI to make a smart guess about data it hasn't seen. This is the gap between a simple lookup table and true machine learning. A common error is assuming a model is smart just because it remembers the training data perfectly. To move beyond lookup tables, we use weights. Think of a weight as a knob that determines how much importance we give to a specific feature. Instead of matching strings, we convert our features into numbers. For example, we can represent red as 1 and orange as 0. The weight is a number we multiply by the input to influence the final answer. This is the fundamental building block of every neural network. A score of 0.5 doesn't tell us if it is an apple or an orange. We need a threshold, which acts like a yes-no switch. If the score is above 0.4, we call it an apple. Otherwise, it is an orange. This is a primitive version of an activation function, which decides if a neuron should fire. A frequent mistake is setting the threshold too high, which makes the model too conservative and always predicts the negative class. How does the AI know it is wrong? We use a loss function, which is like a teacher telling a student how far off their answer was. If the target is 1 and the AI predicts 0.5, the error is 0.5. We calculate this by subtracting the prediction from the actual target. The goal of all machine learning is to minimize this loss value until it gets as close to 0 as possible. Learning is an iterative process of guessing, checking the error, and adjusting. Imagine trying to find a right temperature for a shower by turning the knob slightly left or right. We repeat the prediction and loss calculation many times. In each cycle, we check if the loss is decreasing. If the loss stays the same, it means the model has stopped learning or the learning rate is wrong. To reduce loss, we update the weight. If the prediction was too low, we nudge the weight up. If too high, we nudge it down. We multiply the error by a small number called the learning rate to ensure we don't overcorrect and jump past the perfect answer. This process is a simplified version of gradient descent. A common pitfall is using a learning rate that is too large, causing the model to oscillate wildly. Now we combine everything into a training loop. We iterate through our numeric data, make a prediction, calculate the loss, and update the weight for every single example. This is called stochastic gradient descent when we update after each example. The model slowly carves out a mathematical relationship between the input and the label. Notice how the weight evolves as it sees more examples of apples and oranges.
After training, we must test the model on data it has never seen before. This is the true test of intelligence. Can it generalize? We pass a new input through our final weight and the activation threshold. If the weight has been tuned correctly, the model should predict the correct label, even for a value it didn't see during training. Never test your model on the same data you used for training, as that is just memorization. We have just built a tiny single neuron model from scratch. We went from raw data to a mapping, introduced weights and thresholds, measured error with a loss function, and optimized using a learning loop. This exact cycle, predict, calculate loss, update weights, is what happens inside the largest LLMs in the world, just with billions of weights instead of one. You now understand the fundamental engine that powers all modern artificial intelligence.